Good afternoon, everybody, and welcome to our first Energy Institute lecture. We are very happy that we're going to start the 2023-2024 the series of distinguished lectures at the Energy Institute. And I hope you have seen the programs that we have put together. It looks like something that we're very excited and looking forward to. And we're also very excited today to welcome back, in fact, Professor Dhir. It's our first, it's, I guess, the most appropriate kickoff speaker for the series, and Professor Dhir, who has had a very distinguished career spanning over 5 decades, so it gives me great pleasure to introduce him here. He's a distinguished, in many ways, professor in the Department of Mechanical and Aerospace Engineering at the University at the UCLA, where he also served for an amazing period of almost 14 years as the Dean of Engineering. This is quite a feat, and he has made a number of major contributions as a dean, apart from his seminal contributions in research, as I'm going to highlight. So he holds a Bachelor of Science degree from Punjab Engineering College in Chandigarh, India, and the Master of Technology degree from the IIT in Kanpur. And he received his PhD from the University of Kentucky, and then went to the faculty of UCLA back in 1974. So before many of you, I guess before most of you were even born. That tells us something. And he's a fellow, of course, of many societies and had many awards in his career. He's a fellow of the American Society of Mechanical Engineers and the American Nuclear Society. He received the American Society of Mechanical Engineers Heat Transfer Memorial Award in the science category, and also the Donald Q. Kern Award from the American Institute of Chemical Engineering. As his research is at the interfaces, heat transfer. We'll talk about it, obviously, central to many engineering disciplines, and the mechanical, aerospace, chemical engineering, and beyond. He received the 75th anniversary medal from the Heat Transfer Division of the American Society of Mechanical Engineers. He was recognized in 2013 as the Educator of the Year by the Engineering Council. He has been serving on the National Academy of Sciences Committee on Lessons Learned from the Fukushima nuclear accident for improving safety and security of U.S. nuclear plants, including spent fuel pools, obviously, because heat transfer again and the concept of heating, as we know, is central. Boiling in particular is central to many aspects of what we do in everyday life, and it has important implications both in space and nuclear aspects as well. He has been conducting experiments about understanding the concept of microgravity boiling, right? Which perhaps he can explain to us at another lecture. We can bring him back, right? So he has been recognized in many ways. He received the 2004 McJack Memorial Award, which is a joint award between the American Society of Mechanical Engineers and the American Institute of Chemical Engineers, very prestigious award, and was selected to deliver the Thurston Lecture of ASME back in 2008. He was, for all his achievements and for his immense contributions in boiling heat transfer and nuclear reactor thermal hydraulics and safety, he was inducted to the National Academy of Engineering, and also was named a Hagler Fellow. He came to Texas A&M as a Hagler Fellow back in 2009. And if I can say something about Professor Dhir, is that his passion for, spanning a career over 50 years, his passion for research and education has never been evaporated. So, and I think it's going to demystify for us a novel concept over the last 4 or 5 years for flash evaporation and phase separation, desalination. Desalination is one of the central things and challenges, United Nations challenges, so that we are facing, because water is as equally important as energy. So we live in energy transition, but the next big challenges that the world is facing at the moment is water, and desalination is a key technology. So anything that can become more efficient than current technologies like reverse osmosis is bound to be important. So please join me in warmly welcoming Professor Dhir.
Thank you, Edward, for that kind introduction. Good afternoon. It is my great pleasure to share with you some of our recent work on development of a novel concept for flash evaporation and phase separation to achieve desalination. This work has been supported for the last 2 or 3 years by National Science Foundation. And Professor Banerjee here at UCLA is collaborating with us on this. And so you see, this is a very different way of achieving desalination than other concepts we have. The concept is that we have salt water heated in a solar pond. So we are using solar energy to heat salt water. That water from the pond flows through a single tube or multiple tubes through a pair of injectors that are placed tangentially on a vapor separator tube. As the water flows through the tube and through the injectors, the pressure drops because of friction initially. When the pressure is such that the saturation temperature is lower than the liquid temperature, liquid becomes superheated and flashes. With flashing, you have now vapor and liquid both, and that introduces acceleration pressure drop as well. So when this two-phase mixture flows through these injectors, which are located tangentially, because of the centrifugal force, liquid is pushed out and the vapor comes as a core in the middle. So you see on the left-hand side of this little point was
Within March, it was done.
See on the left-hand side is kind of a three-dimensional view of the vapor core forming in the middle of this separator tube. We have a retrieval tube that is inserted into the vapor core so that the vapor from the core is now sent to a condenser where cold water is flowing through the tubes and vapor condenses, and that vapor is your potable water. And potable water can be pumped back to wherever you need it. And the water that is separated in the separator tube is gone back to the solar pump. So this is the concept. And the key power needs are running the pumps because the flow through the system is as a result of the pressure difference between the solar pump and the condenser, which would be operating at a pressure lower than 1 atmosphere. There are a number of existing technologies for desalination. That is multi-effect distillation, multi-stage flash evaporation, reverse osmosis. Reverse osmosis uses membranes to separate pure water from saltish water, and this is quite popular. However, this requires quite a bit consumption of energy. Then multi-stage flash evaporation, there you use low pressure steam to heat salt water, and then the salt water flashes when the pressure again drops below a certain value, and then the saturation temperature is lower than the saline water temperature, it flashes. The vapor that is produced is sent to a demister to get rid of droplets, and then the vapor goes over a condenser to form potable water, and in turn, saline water is heated. So this is the process. Multi-effect distillation is similar, but in this case, seawater is sprayed over a heat exchanger tubes. These heat exchanger tubes carry steam, so steam condenses, and the energy that is released is utilized to heat the saline water. Hence, as the pressure drops, saline water becomes superheated, flashes, and vapor is produced. That vapor goes through a demister to get rid of droplets, and then the vapor is sent to a heat exchanger and the process repeats. So my talk is organized. First, I give you a brief history leading to this concept. We started with just simple phase separation in the absence of gravity. Here, this work started when President Reagan had Strategic Defense Initiative in 1980s, late 1980s. At that time, the idea was to have a nuclear power plant in space. And to produce electricity, one of the concepts was to use Rankine cycle. In Rankine cycle, you produce steam. And now you have to separate steam from the water. In normal gravity helps you separate the two. But in space, there is no gravity. So we had to come up with a concept to separate water from steam. So here we developed this phase separator. And subsequently, we use this concept of swirl flow for enhancing single phase heat transfer and two phase heat transfer. Then I'll come to the current concept and what we have demonstrated. And lastly, give you some simple cost analysis of producing potable water from seawater using the concept. So going back to phase separation in the absence of gravity, what we proposed was that we place a set of injectors on the separator tube. These injectors were pushing two-phase mixture, air and water, or steam and water, tangentially into the tube. And they were also inclined at about 70 degrees to the main axis so that we impart axial momentum to the two fluids as well. As the fluids come out of the injectors, again centrifugal force pushes the liquid out. Gas is formed as a core in the middle, and we take the gas out through a retrieval tube, or that time we call it a vortex finder, and so that you're separating the two. And the liquid goes out and goes to the main source. This is a picture that was taken in 1980s. And you see in the middle is the gas core. On the left-hand side is a vortex finder or retrieval tube. And you can see the gas core just feeds into that retrieval tube. The key parameter that one needs to know is how long is the core, because you want to adjust your retrieval tube according to the core length. And we found that the core length was dependent both on the superficial velocity of the liquid as well as superficial velocity of gas or vapor. So as we increase the superficial velocity of the liquid, tangential momentum increases. As a result, the core length increases. As we increase the gas superficial velocity of the gas, now some momentum is lost in pushing the gas out and gas in and with liquid out, so the core length decreases and subsequently it starts to increase. So this kind of information is needed to adjust your retrieval tube. Next, we moved on to, so that work was funded by Strategic Defense Initiative. Then we said, okay, let's use this swirl flow enhancement for single phase flow. So we got funding from Gas Research Institute when they wanted to improve heat transfer in their heat exchanger tubes. So again, here we have a set of 4 injectors placed on a tube which would be electrically heated, and a single phase liquid or gas enters through these injectors and a tangential momentum is created. And we define tangential momentum as a square of mass flow rate of the injected fluid divided by the density of the fluid in the area of the injectors. And then there's a total momentum transfer rate, which is based on the total mass through the tube, because there is some axial flow as well. So on the left-hand side, you see the ratio of Nusselt number, which is a dimensionless heat transfer coefficient, and non-dimensionalized with that for fully developed flow. The triangles you see are for a single phase axial flow, and you can see within about 5 to 6 hydraulic diameter, then enhancement to developing flow dies down, and now you have a fully developed condition. But with tangential injection, we find that the enhancement near the inlet increases with the momentum ratio, and for momentum ratio about 5.2, we got an enhancement of factor of 5. And this enhancement decays but persists up to about 70 hydraulic diameters. That's quite long. Then we wanted to see why swirl flow enhances heat transfer. What is the mechanism? So first thing is that we measured the temperature profile in the tube, and we found that because of the centrifugal force, colder fluid was pushed out, and as a result, the temperature away from the middle of the tube was less than that at the middle. And so these data points show the temperature profile with swirl flow. And the dotted line is turbulent flow fully developed in a purely axial. So you see in this case, you find there's quite a bit depression in the temperature and very steep gradient near the wall. Then we wanted to have a correlating parameter. Momentum ratio is one way of doing it, but we define swirl intensity. Swirl intensity is integrated value of the rate of tangential momentum divided by the rate of axial momentum. So swirl intensity was the key parameter that we used for correlation of the data. And on the left-hand side, you see a plot of enhancement in heat transfer as a function of the swirl intensity. As we increase the swirl intensity, heat transfer improves. For a swirl intensity of about 5, you can see the heat transfer is enhanced by more than factor of 2. And this was at, these data were obtained at axial distance greater than 6 hydraulic diameters. Then we found that this enhancement would be related to the maximum axial velocity in the tube. So when we normalize the data with maximum axial velocity in the tube, we found it correlated well with the swirl intensity. So indicating to us that swirl enhanced or increased the axial velocity near the tube surface. And again, you can see that the enhancement increases as swirl intensity is increased. Then we measured the turbulent intensity in the tube using an anemometer, and we measured 3 components of turbulent intensity and integrated over the cross section of the tube and normalized with that average axial velocity. And on the left hand side, you see the turbulent intensity as a function of swirl intensity, and that it increases almost linearly with the swirl intensity. So what it tells us that not only swirl increases axial velocity component near the wall, but it also increases turbulence intensity, which improves mixing and improves heat transfer. So there are two mechanisms of enhancement of heat transfer this way. Increased axial velocity, increased turbulence. And we got patent for this work, and it was, as I said earlier, supported initially by gas research institute. Then after this, we said, why not two-phase heat transfer, boiling? And boiling is already associated with very high heat transfer rates, but with swirl, could we do better job? And in boiling, the critical heat flux occurs when the combination of vapor bubbles on the wall takes place because the vapor production rate is falls short of what is removable. So bubbles start to accumulate on the surface and blanket the surface with vapor, and you have a drastic reduction in heat transfer. So in these experiments, we installed a pair of injectors at different locations along the tube, and we could inject fuel to the engine. Now I must tell you, students are here to tell them the story. I gave this idea to one of my master's students. I said, go ahead and conduct this experiment. And he conducted the experiment, came back, no, heat transfer is not enhanced, it is decreased. So I said, why, what's happening? Decreasing is a correct opposite to what I expected. So then I went back to the lab and looked at how he was doing the experiment. When he was drilling holes in the tube, he was thinning the tube wall. And this was electrically heated tube. So locally he was creating hot spots, and that was triggering the early burnout heat. So once we fix that problem, he has critical heat flux much higher with soil. So these things happen in the experimental work, and this work was funded by Office of Fusion Energy in the Department of Energy. So here is an enhancement for single phase enhancement. Again, now we use liquid rather than a gas as a function of axial distance for different momentum ratios. We see the same behavior, that enhancement is much higher with tangential injection and lasts for long distances. And as compared to axial flow shown by triangles, axial flow very quickly becomes fully developed flow in about 6 to 7 hydraulic diagrams. Let me look at the two-phase boiling heat flux. And here the circles are purely axial flow, and the triangles are the data when we have tangential injection. You see with tangential injection in partial nuclear boiling, heat transfer is enhanced quite significantly. In fully developed nuclear boiling, there is not much effect, but critical heat flux with injection is higher than that for pure axial. This is for axial location about 6 hydraulic diameters from inlet. And next we looked at 13 hydraulic diameters from inlet. Similar behavior. Critical heat flux is again higher with swirl than it is for pure axial flow. So here is the critical heat flux enhanced as a function of inlet subcooling, which is a kind of a quality, inlet quality. More subcooled liquid is more negative quality. And we plotted here for 3 different ratios of injected mass velocity versus total mass velocity, because we were putting liquid axially as well as tangential. So as you have more injectors, you are putting more liquid tangential. So you can see when the ratio of the injected to the axial flow was about 0.4, the critical heat flux was enhanced by about 60–70%. This is a big increase. When I showed this result to the person at DOE, he says, this kind of science I am not interested in. See, people are not really looking forward to, they want something traditional. And here is the evidence of what's going on. This left-hand side is a tube placed at the exit of the heated test tube. And you see with pure axial flow, the bubbles are kind of distributed uniformly in the tube. When we have swirl, the vapor bubbles are clustered in the middle, and you see a kind of a string of bubbles. So demonstrate that the swirl flow is really effective in pushing the bubbles away from the ball. So this is the enhancement in critical heat flux as a function of the fraction of the liquid that is injected tangentially. When we inject 80% of the fluid injection tangentially, we find the enhancement is about 70% in critical heat flux. Now, in this world, there is no such thing as free lunch, only except what we got to drink. And so you have to pay some penalty. Because most often people claim that they enhance heat transfer without paying penalty. There is always something. So then we said, okay, because the pressure drop to the injectors is more, so we are paying additional cost, pumping cost. So this lower curve, the squares, is enhancement in critical heat flux on a constant pumping power basis. So there, our enhancement, maximum enhancement occurs when the tangential velocity to the axial velocity ratio is about 40%, and this enhancement reduces to 25%. So 25% enhancement in critical heat flux is occurring without paying any penalty. So this is, I think, quite valuable. Next, let's go to the current concept. Current concept, because in the lab we don't have a solar pond, so we use as electrical heating. In this case, we have a primary tank, and to which we take the liquid, goes through a heated section to heat it to a certain temperature, and then it flows through two injection tubes, which are connected to two injectors, and the injectors are placed on a separate tube. As the liquid flows through the tubes, and again the pressure drops, saturation temperature drops, and when it is less than the liquid temperature, liquid gets superheated and shrinks and produces vapor. So that is happening in the first stage. The vapor core forms, and the vapor from the vapor core is taken out. However, there's a problem. There's some droplets get entrained in the vapor. So we place a second stage, you see, next to the first stage. So the vapor coming out of the first stage is fed to a second stage, so that we can get rid of any droplets that are entrained. And the second stage, vapor from the second stage goes to the condenser and gives you the potable water. And liquid that is separated goes to a secondary tank, and then the primary tank, and all that liquid is sent back to the primary. Okay. So the tubes that we are using are very inexpensive. Those are plastic tubes or polyvinyl tubes, and the injectors are also made out of aluminum, and they are placed on these tubes. For the first stage, the tube was 20.6 millimeter in diameter, and the injector diameter was 6.35 millimeter. For the second stage, we increased the diameter of the injectors to 9.53, and the key reason was to reduce the pressure drop. As the vapor flows through the retrieval tube, there's a pressure drop. So this is a picture of this vapor separator working. On the right hand side, you see the vapor core, and the left in the middle you see dark, that is the retrieval tube from which vapor is removed, and as vapor covers the vapor core covers the tube so that minimize the number of entrained droplets. The upper is for a lower flow rate, and the lower curve is for a higher liquid flow rate, and you can see as consistent with the earlier result, vapor core is longer for the higher flow rate. Now, before I go further, what the correlations are, I will want to define certain parameters. How do we know this system is working the way it is working? What is its performance indicator? So for that, we first define a thermal conversion efficiency. Thermal conversion efficiency is simply ratio of the maximum possible temperature drop. You have inlet temperature of the liquid, and then you have temperature of the liquid at the injector exit. So that temperature would be more than the saturation temperature based on the exit pressure. So we define delta T injector, and it's divided by the maximum possible temperature drops. That would be temperature of the liquid at the inlet minus the saturation temperature of the pressure at the exit. That exit pressure is the condenser pressure. So this is thermal conversion efficiency, then phase separation efficiency. How better we are doing in getting rid of these droplets. So the droplets, you don't want them because those are salt water. And that would reflect on the quality of the water that we produce. So we want to determine phase separation efficiency. That is the ratio of mass flow rate of the condensate divided by what you collected, the condenser, mass flow rate in the condenser. That is higher than the condensate because of the entrained droplets. So that is condensate plus entrained. Now, unless you measure the salt concentration, you don't know how much is the entrained water. So in this case, having salt water helped us to find this entrained water because it served as a tracer as well. So if you make a mass balance on salt, so you see m dot of condenser times the salt concentration in the condenser is equal to the mass of condensate times the salt concentration in the condensate plus mass flow rate of the entrained liquid times the salt concentration in the container. In the vapor, salt concentration is 0. So we find that mass of flow rate of the entrained liquid is simply mass flow rate of the condenser times the ratio of the salt concentration in the condenser divided by salt concentration in the entrained liquid. In entrained liquid, salt concentration is the same as your original water. In the condenser, you measure it. So what is the salt concentration? So knowing the entrained water, we can calculate the mass flow rate of the condensate, and from then you can determine what the separation is. Another parameter we define is a collection efficiency. You know, when we separate the liquid and vapor, some of the vapor goes with the liquid that we took up. So that is your product which is being wasted. So we define collection efficiency, which is mass flow rate of the condensate divided by the mass flow rate of vapor. So these were the indicators of the performance of the system. So next we wanted to see that how these parameters we measure compare with simple-minded predictions. So the quality at any location is simply product of specific heat and the difference of liquid temperature at the inlet minus the saturation temperature at the local pressure divided by the vaporization, and quality can be related to the void fraction, to density ratio and a slip factor, and the pressure drop, as I said, occurs because of friction and acceleration. For friction pressure drop, we simply used a two-phase friction factor, and acceleration pressure again is related to the quality and the work. And the slip factor we assumed to be 1.5. Based on that, we plotted what we expect the temperature and pressure distribution would be to the injection tubes and the injector passages. So here on the left-hand side, you see the solid line is the pressure distribution with the squares, and the upper dotted line is for the liquid temperature, and the lower dotted line is the saturation temperature. So difference between liquid temperature and saturation temperature due to the superheat that is driving the formation of vapor. And we made only 2-point measurements. One was at the inlet to the injection tubes, and the other was at the exit of the injectors. And those are the solid points you see. And they are not far off from those simple-minded predictions. So that kind of told us that we were kind of in the ballpark, but it was a more sophisticated model way to do some of the work. This is very simple effort. On the right-hand side, you see a plot of quality and void fraction. And at the exit of the injectors, the quality can be about 5%, but the void fraction can be about 95%. So most of it is vapor. Here are the performance data. Left-hand side is thermal conversion efficiency as a function of flow rate. As you can see, higher thermal conversion efficiency is around 95–97%. And however, thermal conversion efficiency decreases as we increase the flow rate. Now you ask why? Because as you increase the flow rate, you are producing more vapor, so there's a more pressure drop to the evaporation. So that affects your saturation temperature in the exit, and thereby thermal conversion efficiency goes down. Next is the phase separation efficiency that does a similar thing. As we increase the flow rate, separation efficiency goes down. More vapor, more liquid droplets are drained, but you see that separation efficiency as high as 98–99%. Here's the data for thermal conversion efficiency as a function of superheat. Again, as we increase the superheat, thermal conversion efficiency decreases. Key reason being the same, that you produce more vapor, more pressure drop in the evaporation. And the right-hand side is phase separation efficiency as a function of available superheat. And interestingly, phase separation efficiency increases as we increase the superheat. With more vapor inertia, we are entering less droplets. These are the correlations for the thermal conversion efficiency as a function of your quality, pressure at the exit, and the mass flow rate. And the range of parameters were a factor of about 4. And similar correlations were developed for phase separation efficiency. Again, as you can see, the phase separation efficiency equals to 99%. And key message here is this two-stage system. Our initial salt concentration in the tank was 2.5%. In the water that we collected in the condenser, the salt concentration was 0.02%. This is like potable water. So in a way, we have demonstrated that we can take salt water from sea and make it a potable water. And just that simple system. Next, the question was to do some detailed investigation of the flashing phenomena. And here we built a square glass tube. On that, we put a capacitance probe so that we could determine the void fraction. We also took high-speed videos to see the dynamics of the phenomenon. And we used both seawater and plain tap water in these experiments. From these videos, we could also get limited single bubble flow. This is a sketch of the square tube, Pyrex tube, which we use for squats tube actually, for installing of capacitance probes, and we have pressure and temperature taps. And again, as I said, with the capacitance probe, we could determine the void fraction. Here's a big picture, photographs of the various flow regimes along the flow direction. The top one is for tap water, and you see in tap water is the direction of flow. And you see the flashing has occurred, the bubbles are formed, and then you see flow regimes developing and non-void fraction in the middle. And then you see also in the last one, more activity of bubbles near the wall. Now, when we go to seawater, we see very different behavior. I never expected it. You see, the bubbles are formed, they are clustered in the middle, not at the walls. And those clusters continue to persist, and those bubbles don't merge. So I don't have an explanation why it happens. But this was the difference with seawater. This is a video of the room. These bubbles stay the same. This cluster is there, and also you see there is no activity on the walls for this case. Whereas for tap water, there is activity in the walls. So this kind of information we need for better modeling. And this is a set of videos or pictures from the measurements of high-speed videos. And we are plotting here on the left-hand side the pictures of the flow regimes as they develop in the axial direction for different flow rates. On the right-hand side, we have void fraction as a function of distance along the tube for different flow rates. So what we find is that void fraction increases in the direction of flow as more flashing occurs, and also as the mass flow rate of the liquid increases, the void fraction decreases. And the pictures on the left-hand side plus the void fraction measurement on the right-hand side now can be used to a better statistic model for the process. This is a measurement of a single bubble flowing in this flowing liquid, and as you can see, the bubble seems to grow linearly with distance time, and as we increase the superheat, the rate of increase of bubble size is increased, as that's what we expect. Then we did some modeling as a first step in the numerical simulation of the flash evaporation phase separation phenomena. Here we're just looking at a single bubble in a pool, but with seawater, and pressure could be decreasing with time. So basically, we solve the inertia equation or the momentum equation. We account for the pressure difference because of the capillary. We include the viscous stresses. Then we solve for the energy equation and also the salt concentration. At the interface, preferentially, you would take from the salt solution, vapor goes into the bubble, but the liquid is left behind. So with time, liquid concentration near the interface increases. Solid dissolved solid, or the salt concentration increases at the interface, and salt now diffuses into the bubble. So this process needs to be understood. And here is the result for a bubble radius as a function of time for different salt concentrations. As you see, as we increase the salt concentration, the growth rate of the bubbles decreases. So presence of salt decreases the effectiveness of the process. Now this is one just comparison. Solids are the prediction from the model. The dotted, the circle open circuits are the data from the videos over first 3 or 5 milliseconds. And you can see the comparison is okay, but it's not as we would expect. Next, we made some simple cost analysis, and these are very preliminary. And to see how expensive this potable water that produced would be with this concept. Again, we are using electric power, so the cost is based on the electric power. Main source of energy loss is the condenser water, because the vapor you condense releases latent heat of vaporization that is picked up by the cold water, which is flowing through the tube. Now, if you throw it away, you have lost that energy. So you want to use that energy that is deposited into the cold water going to the condenser tubes. So we developed a multi-stage process where the water exiting the condenser goes to the second stage, where we go through the same process again and so on. So we did up to 6 stages. And here are the results of that. Because in each stage we are increasing the amount of vapor that we produce, although amount is less because the rate at which water is flowing to the condenser tubes is less than the rate at which the water is entering the flash. So you see that the first stage we produce only 20.25 grams per second of vapor, but by 6th stage we double the amount of vapor that we produce. And the cost or the electric power that we produce decreases by a factor of almost 50. So for 6 stages, we are consuming about 13 kilowatt per hour per meter cube of water that is produced. Now, if we use 6 cents per kilowatt hour, that is 78 cents per meter. Now, if you increase that to 10 cents, 15 cents, this cost will go up. So this is based on how expensive the electric energy is. But again, here in the lab, we are using electric power. But if I were in the field, I would probably be using solar power. So, and finally, to conclude, I hope by now you are convinced that swirl flow is an effective mechanism or effective approach for heat separation and for enhancement of single and two-phase flow, heat transfer. Flash evaporation combined with swirl flow is an effective and viable concept for desalination. Limited cost analysis of the modular system shows the process is competitive with other capital-intensive processes, and we can make further advances and even increase the number of applications to be developed by the scale. Thank you.